YouTube. All right, so welcome back, folks. Thanks for coming back, I should say. Or wait, well, we're missing a huge chunk of people, but they left their stuff here. I suspect that means they'll come back. So I apologize for the somewhat herky-jerky nature of skipping around and things. The problem is that I don't know exactly who I'm talking to. Like when I do intro workshops, I just assume no one knows anything. I assume some level of knowledge, but I think there's either folks who either haven't had it before or it's been a while, and so I'm trying to feel my way through this. So if I don't talk about something, like I forget to define REML, and because I'm assuming that you know it already, please stop me and make me clarify, because I am happy to do that. So some of the sections of the notes that I skipped over this morning, we can skip the SEM stuff for now because that's not immediately relevant. But I do want to make sure that I hit the idea of significance testing and effect size for the fixed effects versus the variances, because that's something that is easy to screw up if you don't have it formally presented to you. So I wanted to pick up there, if that's all right. So I'm on slide 37. So I've said some of this stuff already, and I just want to make sure that because it is sort of things that I'm assuming you know how to do, that that's actually the case. So we're in Lecture 1, slide 37. So assessing the goodness of the model is the topic here. So the idea of how do you get measures of significance and effect size. And the answer depends on whether you're talking about the means model or the variance model. In other words, fixed effects or random effects. So model for the means is the fixed effects, so the effects of predictors that everybody shares. So significance tests do not require any kind of log likelihood comparison. If you have a fixed effect, you can stare at the p-value that shows up on the output. And that is known as a walled test. You can get univariate or multivariate versions. The next slide will go over what those mean. Effect sizes then can come from a couple different ways. You can always take the values on the output like T's and F's and convert them to things like Cohen's d. You can also do reductions in variance. And I want to give you two different complementary ways of talking about reductions in variance from fixed effects. Pseudo R-square, which we've talked about a little bit, and then also total R-square, which we have not. When you're assessing the model for the variance, the idea of what effects need to be random and how do you know if it's good enough, that's when you do need to do some kind of -2 log likelihood test. And so significance tests for new random terms, for new variances, such as a variance of an intercept, the variance of a linear time slope we did in the previous example, because variances can't be negative, we can't stare at the p-value that shows up on the wall test. We have to do a -2 log likelihood comparison. Effect sizes, though, are less commonly provided, but I would argue just as useful when it comes to assessing variance. So because random effects don't explain variance, they just partition it, we don't do pseudo R-squared. You can do a couple of things instead. One is this idea of a random effect confidence interval. And so I just wanted to throw this up here as the analog to what you would talk about in terms of the model for the means. This is effect size in the model for the variance. So if you choose to report these in your papers, you'll have to explain what they mean, because this isn't something that everyone will be familiar with. But for any term that has a fixed effect and a random effect, you can calculate this interval where the center is the fixed effect. And then you can go 2, and this is basically a standard deviation around it. So then you're talking about the spread of the term across the sample. So for instance, if I have a slope on average that is +1, so on average for every 1 unit change in x, y goes up by 1. But I have a significant random slope variance around it, I might want to know whether my interval is just from 0 to 2, for instance, in which case I would talk about it as that everybody varies in how much they grow. Or if it's 1 on average, does that mean that it goes from, -10 all the way up to +11? If that's the case, then I have some people who are predicted to decline and some people who are predicted to grow, even though people grow a little bit on average. So it helps to convey in a more meaningful term just how to talk about variability in your sample. So that's what I would do if you're trying to give some kind of version of effect size for a variance component. The significance test that you do is not an effect size. It's just a test of whether or not the new random variance is different than 0. So the letters that you get on your output, this is another way that programs will differ when you're testing fixed effects. In small samples, meaning small level 2 samples, you are going to want to use some kind of denominator degrees of freedom. So this shows up in SPSS as the only option. You get something called Satterthwaite. In my SAS code, I use Satterthwaite for comparability, but there's other ones such as Kenward-Roger. That's the most optimal one, and that's the one that's been recently introduced into Stata that was also in SAS. If you have a program that uses some kind of denominator degrees of freedom, then what's going to show up on your output for fixed effects is a T when you're testing one fixed effect, and if you're testing multiple fixed effects at the same time, it's an F. So this idea of testing multiple fixed effects at the same time is what's known as a multivariate wall test. And specific examples of this are when you have, say, a grouping variable like in an ANOVA, and you get an omnibus main effective group that has more than 1 degree of freedom, that's a multivariate wall test. Another specific example that you will be familiar with is in regression when you get an F test for the model, whether the model as a whole accounts for variance. That's another type of multivariate wall test. And so you can ask for these in any of your program. So that means that when you're looking at fixed effects, you never have to deal with -2 log likelihood at all. You can do with this instead. If you're dealing with a program that does not use denominator degrees of freedom, it assumes that it's infinite instead, such as the only option you get in M+, and in Stata by default, then you get a Z for a single fixed effect, or a chi-square for a set of multiple fixed effects. So T squared is F, Z squared is chi-square. So that's how they relate to each other. So I tend not to report the specific degrees of freedom that are given on the output, but I will mention as the start of the results section which method I used. So I might say something like, all models were estimated using residual maximum likelihood in SAS mixed with Satterthwaite denominator degrees of freedom. I would say a sentence like that just covers, in terms of a replicability standpoint, if somebody wanted to get the same numbers as me, how I got them. Okay. Pseudo R-squared, then we talked about this. So any fixed effect that you add to the model, its job is to tackle one or more of the variance components. Should usually try to be one. We'll talk more about that later this afternoon. Another way that you can talk about effect size, though, is to try and think of the model as a whole and how much variance is accounted for when you put it all back together again. And that's the idea of total R-square. So you can take, in any program, you can ask it to save the outcome that is predicted from the model fixed effects as a new column. That's one line of code in all of the programs that I deal with. You can take that new column of model predicted outcomes, correlate it with the real outcome, square that correlation, and that's our square. So in models that have a lot of variance components, this can be useful. Rather than trying to keep track of each separate variance component and having it wiggle around on you, it's also intuitive for readers who may not be familiar with multi-level models, because then it is more like the R-square you get in regression. And it's a way to think about what is like the real absolute amount of variance that's been explained by these predictors. So I would recommend potentially reporting both of these as complementary pieces of information. And in my examples, I have little macros that do both of these for you. But because there's so many different kinds of R-square in the land of multi-level, you have to say exactly which one you used. You can't just say R-square, because there's level-specific R-squares, there's pseudo R-squares, and there's total R-squares, and they all mean something different. So pseudo R-square is a per pile R-square. So like in our example, we said we got 34% reduction in the level 1 residual variance specifically due to time. But we can also talk about what is the total effective time in the model by looking at total R-square. So once we add another fixed effect, we'll get examples of both of those. Okay. So any questions on any of that? Okay, So then on the variance side, this is where we do our -2 log likelihood. So we did an example of that earlier, where no matter if you're in REML or EML, both of which are full information, remember, we would take a model with fewer parameters minus the model with more, and that gives us a positive value. That positive value is then compared to a chi-square distribution with degrees of freedom equal to the difference in the number of parameters. So you can do this with an option called LR test and Stata directly. I built a little macro in SAS, and I also have an Excel spreadsheet that you can download as part of your download packet that uses the chi-dist function. So for any of those, you can get an exact p-value rather than just getting a critical value. One thing to keep in mind about what the -2 log likelihood test means, it depends on the way you think about the models to be compared. So anytime you're trying to make your model bigger, you're adding things to it, your options for the result of this test are either better or not better. If you add things, it can only get better. The worst that can happen is that it stays the same, in which case you would say that it's not better after you added things. If you think about it from the opposite perspective, if you have a model where you're trying to make it simpler, then your options is that by taking away parameters, you either made it worse or not worse. As an example of when you think about it that way, that's the logic of model fit in SEM. You have the best possible model as the saturated model where you let all the means, variances, and covariances be whatever they want. You then fit your factor model. Your goal is to say that your model fits not worse than the best one. And so in that case, you want a non-significant chi-square for the difference in fit. And the same thing would be true here if we started with, say, an unstructured variance model and we wanted to see whether or not it was adequately reproduced by the patterns introduced by our random effects. It would be the same idea. So better or not better if you're adding things, worse or not worse if you're thinking about it as being taken away. And then just a note here on two other things that people sometimes report, which are variations of -2 log likelihood that correct for the number of parameters. In all programs, these are phrased as smaller is better. So there is no distribution, just smaller is better. That's it. So we did EML versus REML, and we did that. Okay. So, yeah, now we can start new stuff. Yes, sir. That's not a coincidence. Mm-hmm. It would not necessarily be a per pile. I think it would be whatever term the F statistic is referring to. So there are formulas. You can ask the Google how to go from T or F to D, and so those are the same formulas that you can use. I believe that you can. I've never heard otherwise. Let's put it that way. So to the best of my knowledge, you can. All right. Other questions? So we had a couple questions over the break about sort of how does this apply to me kinds of questions, which I always like. So the way that time gets put into your data depends on the context of the study and the sampling design. So we looked at sort of this type of change here, which we would call growth curve modeling, where you're trying to see what kinds of fixed effects of time that we have. So far we just have linear in the model, but we know we need something bendy. Where the model is trying to capture the fixed effects of time or trying to capture the average trajectory of change. On this side of within-person fluctuation, if we put a linear effect of time in the model, it's not going to help us. In this picture on the right here, let me get my laser pointer. In this picture on the right, there is no linear effect of time. So this would be a situation in which the fixed linear would not be significant because there's nobody going up or down on average, and everybody's going not up or down to the same extent. So putting time in a model for these data would not make any sense. It wouldn't help anything. Now, what these data likely do need is going to be a little different. One way that time can sneak in here is not as a function of time and study, but other kinds of things like seasonal effects or day of the week or time of day or those kinds of things. So if we take the example from earlier, a case of the Mondays, what if you found that negative affect was higher on Mondays? We could incorporate that into a design like this, both as a fixed effect and a random effect. So at the simplest case, I could have a dummy code for whether or not it's Monday. And the rest of the week is the 0 and 1 gets the Monday. If I put that in the models of fixed effects, that asks, on average, is there a mean difference between Monday and the rest of the week in the outcome? A random effect, though, then would allow the size of the mean difference to vary across people. Some people really hate Mondays, and some people might hate them less. So the average hate would be the fixed effects, and the extent to which people differ in their hatred of Mondays, that would be the random effect variance around it. The other thing that this picture also illustrates, which we're not going to get a chance to do in this workshop, but I want you to know that it's out there, is individual differences in the extent of within-person fluctuation. So like this blue person up here doesn't really move very much. This pink person is all over the place. These models, by default, assume constant variance across people in the extent of within-person fluctuation. Everybody shares the same level 1 residual variance that is meant to capture within-person fluctuation. If you're doing a growth curve study, the level 1 residuals represent the why are you off your line today? And it would probably be reasonable that the extent of line offness would be the same across people, because people are differing in the random effects that give them individual trajectories. Over here, the residuals are why are you off your line, where the line is a flat line. And so some people may be really off, and some people may be a little bit off. So the models that you can use to address, to incorporate individual differences in within-person fluctuation and to then predict them with person-level information, those are called location scale models. And they're almost always phrased as predicting the log of the residual variance. So I'll say that again, it's location scale model is the Googling term for that. I also call it a heterogeneous variance model. And that is newly incorporated into M+ version 8. You can do it in SAS NL mixed or any other package that allows you to write your own custom model. And the go-to person on those models is named Don Hedeker. He's at the University of Chicago. That's Hedeker, if you're writing that down. And he has written brand new software, I believe, that is now out to do those kinds of models as well. So if you're interested in describing why some people are more or less consistent in their behavior, that is allowing different residual variances across people. And that's a different kind of model. It's a different extension of a multi-level model, I should say. Sure. So when you refer to those models, you have substantive predictors that are fixed. So people who are higher in emotional stability can be more consistent. Yeah, exactly. So in this type of picture, like if I put in, let's say, narcissism, right? Let's call this like negative affect. Maybe people who are more narcissistic personalities are higher in negative affect. That would give me like the difference in the average for this blue person versus the average for the green. But I could also put in narcissism as a predictor for why this pink person is all over the place relative to this blue person who's very calm or moody. Yes, and that's a time-invariant predictor, but you could also have time-varying things. Like on Mondays, you are more variable than the rest of the week, for instance. Yeah, so you can, in general, you can have predictors of heterogeneity of variance at its level or above. So a level 2 predictor can explain differences in level 1 residual variance. A level 1 predictor can explain differences in level 1 residual variance as well. And they predict the log of the variance so that the predicted variances always stay positive. So in this context, we are examining individual differences in change, but what if it's not linear? What if it's something else? That's what we have to figure out, is how to do that. We did that one. So how familiar are you guys with quadratic effects of time? Yes? You're good? Okay, so if I said that my linear slope is 4 and my quadratic slope is 0.5, put those coefficients in a sentence for me.
What's your intercept?
10.
So at the intercept, your linear slope, the initial trajectory is 4 with an acceleration or deceleration of 2.5 over the time.
2.5 over the time? I said 0.5.
0.5, sorry. Yeah, an acceleration of 0.5 in the slope over the course of 1 year, right?
So very, very close. Very, very close. But the trick, you missed the trick. It's not 0.5, it's twice 0.5. It's twice. This is the little known trick with quadratics. You have to take the quadratic coefficient and multiply it by 2 to talk about what it does to the linear per unit time. But you're much closer than usual. And this is something I didn't stick in here, but I can go over it very quickly in a different lecture if you would like to hear the why. Because we're going to have a quadratic fixed effect. So I'm switching lectures for a second to go into some of my more introductory stuff. So just look up here for a moment. I can give you 2 reasons why it has to be twice. So if we're talking about a quadratic effect of time, we're allowing the linear effect of time to change. To talk about it as how the linear effect of time changes, you have to multiply the quadratic by 2. And there's one reason here that's calculus, because what we're actually talking about is the second derivative with respect to time. And when you take the first derivative with respect to time, the squared term comes down in front. And so the second derivative, which actually gives you the rate of acceleration, is twice the quadratic coefficient. And there's always some people that look at this and go, yes, calculus, yes. And there's some people that are like, calculus, no, no thank you. Here's the other way I can explain it instead, because it's part of the rules of how you would interpret any kind of interaction term, and a quadratic effect of time is just time by time. So in this type of model right here, I have a main effect of x, a main effect of z, and an x by z interaction. This x by z interaction does 2 things at the same time. It takes the main effect of x and it adjusts it based on z, makes it more positive, less positive, more negative, or less negative. It also takes the main effect of z and adjusts it based on x. So it does 2 things here at the same time. If I write our model with the quadratic in the same way, it's like we're missing the other main effect. So there's only one main effect of time, so the interaction term has to do what it was going to do to it twice. So, and if that doesn't make you happy, then because I said so is the only other option. Because math, it is the way it is. So when we talk, in the example that we have here, we have the next step is making it bendy via a quadratic. There are lots of ways to make it bendy. Quadratic is the easiest one. It has its ups and downs, and I would be happy to talk about some alternatives if you're interested, although I hadn't planned that as part of my show. So I'm picking up the example where we left off on page 7. This is 1A. Is this a Pepsi campus or a Coke campus? Or is that not a thing here? No one knows? It's Coke? Okay, well, cheers then. We were Coke and we just switched to Pepsi, but Diet Mountain Dew is not available anywhere. So I've gotten used to bringing my own wherever I go. All right. So I'm here at Model 2C. In the original plotting of the data, this is what the means looked like over time. This here on the left, that looks bendy to me. So I'm going to try and approximate this trajectory by adding a quadratic effect of time. That's an easy way to do it because all software will let you do that. One nice feature of the software for these models, these univariate multi-level models, is that you don't have to define interaction terms as observed variables. You do in M+ and in some other programs, but here, for instance, I can make a quadratic effective age just by putting an asterisk between the two. You can do that in SAS or in SPSS, and the analog for Stata folks is this thing right here, which if you are over 40 is a pound sign. If you are under 40, this is a hashtag. And then I have a whole bunch of other code down here. So these are estimate statements. Are these new? Have you seen stuff like this before? Like these kinds of lines, tests, these lincoms? No? Oh. Well, you're going to love this. No, really. This is one of these things that I wished I had learned way before I actually did. These are ways of making the program do math for you to figure out what the model inside is for any other centering point. So in this example, time 0 is age 18. That means when I get to my output, the fixed intercept is going to be the predicted outcome at age 18. This linear slope is now a simple effect within this interaction. It's the instantaneous linear slope at 18. If I want to know what the predicted outcome or the linear slope is at any other age, the model knows. The model could predict that for me. I just have to ask for it. The way that I learned how to get it at any other age would be to recenter time, rerun the model, and then the intercept and the linear slope would be specific to that new age. Well, to get that for every possible age, I'd have to run the same model 7 times. I'm lazy. I don't want to do that. So I'd rather write out statements like this that do it for me. So these statements here, first off, they create predicted outcomes at any occasion. So the one that is given to you by the model is age 18. The words here refer to the betas that go with them, or the gammas, I guess, in this notation, the fixed effects. So to get to what the predicted mean is at 18 from the model, I need the fixed intercept plus the current value of linear time times the linear time variable plus time squared. So you can tell with the zeros here that this is what the intercept becomes. That's the model intercept is at 18. To get it at any other occasion, you fill in your times. So at 17, it's -1. -1 squared is 1. At 16, it's -2. -2 squared is 4, and so on. So I get not only the predicted intercept at each of these occasions, but the standard error that goes with it, which is nice when you want to make confidence intervals and that kind of stuff. This one is the one that I wished I had gotten involved with much earlier. These are simple slopes. So in the moderation literature, this would be known as probing an interaction term. I hate that word. It sounds very biological. But I would just call these asking for simple slopes. So the model tells me what the slope is predicted to be at any occasion. The one that shows up in the output is the linear slope specifically at age 18, which is where time 0 is. To get to what it is at any other time, I need the linear slope plus what the quadratic does to it. What the quadratic does to it is twice the quadratic makes the linear slope change per unit time. And so in this case, since time is going backwards, these numbers are negative, but it's just whatever time would be at each occasion times 2. So we can see what the model says. For instance, the linear slope was at age 12, as well as what it is at age 18. And the code in SPSS looks remarkably similar. The code in Stata using lincom, you can also do this in margins, I think, looks fairly similar too. So we added just the fixed quadratic. So I'm only interested right now in looking at the solution for fixed effects. So there's my new quadratic. To know how to interpret a quadratic coefficient in terms of the direction, you have to know what the linear direction is too. So just like two-way interaction terms, there's only 4 kinds of quadratics in the world. It takes a linear slope and it makes it more positive, more negative, or less negative. That's it. So you can't look at either of the signs in isolation. You have to pair them together to know what's happening. This pattern right here, this is the linear slope at age 18. It becomes more positive by twice the quadratic at each additional age. So if this is about 14, it would be more positive by 0.28 per year. So I would call that acceleration because the extent of going up is going up. Yes?
Except that our intercept is at the end of the age group, so it's actually accelerating up.
Exactly. It's accelerated to get up to where we are at the end. So if we want to talk about what happens as we go back down, it would be decelerating. So here's the predicted outcomes from the model, and here are the predicted linear slopes at each age. So each of these then differs by exactly that 0.28, twice the quadratic. So at age 12, they weren't increasing significantly on average per year. They were increasing significantly by the end. So they're going more up over time. So the linear slope is positive. It's becoming more positive by twice the quadratic per year. Questions on that? So then effect size. This is a time level predictor, right? Time is level 1 or 2, folks? 1, yeah. So which variance should it have reduced? Level 1 residual, level 2 intercept, or level 2 slope? Yeah. Feel free to gesture. You don't have to talk. What level 1 predictor captures level 1 variance? And indeed it did. So relative to the random linear model that we had before, here's the pseudo R-square. So we had 8.7 down to 8.3. That's a reduction of another 4%. So of the why are you off your line variance that remained, after giving each person their own linear slope, adding a fixed rate of acceleration captured another 4% of that remaining level 1 residual. So it gets tricky to talk about what is the effect of time when we have all of these models adding fixed things and random things. I want to demonstrate total R-square from this model as well. In SAS, it's this statement right here, out PM. In SPSS, it's right here, save equals fixed pred, and that's the name of the new column that gets created in the data set. And predict with XB as an option in Stata. What those lines of code do is generate another column in your data set that is the fixed effect predicted outcome. So just from linear and quadratic time. We can then correlate that predicted column with the real one, square it, and that's total R-square. And so I wrote a little macro that does that too. So the correlation between the outcome predicted just from fixed linear and quadratic time and the real one, that correlation is 0.4. You square that, it works out to be a total R-square of 0.19. So 19% of all the variance in risky behavior, putting it all back together again, is because of systematic change over time. That's all the fixed effects. So where did the random effects go? They did not get included in the prediction. Because they don't explain variance, yes. And so that was actually going to be my next question. Thank you for setting that up for me. So why didn't I include the random effects in the prediction? Because random effects are errors still. U0 is how far off your intercept is, and U1 is how far off your slope is. We don't know why it's off. We know that it is. So the U's are still unexplained variance, and so it's not fair to put them into the prediction here and think of it as explained variance, because you haven't explained anything, you just partitioned it. So yeah, you can do this with fixed effects and random effects in the model, or just fixed. It doesn't matter, because the prediction is only from the fixed. So next question then, does the extent of acceleration need to vary across people? Adding in U2 into my equation here, adding it on the random line. That's a likelihood ratio test. Survey says, nope. So we've got away with a fixed rate of acceleration then in this model. And by the way, this is what the predicted variance at each occasion, how that gets built is all this stuff. But you can see that we have time to the fourth show up in here. So the variance changes time to the fourthedly over time. All right. So there's my picture. So this picture compares the models that we looked at with respect to the fixed effects, where the black line is the saturated means. So that is putting rounded age into the model. That's what we're trying to approximate. The empty model has only a fixed intercept, says there is no effective time. Linear says that it would keep going at the same rate, and quadratic maps nicely on there, because I generated the data that way. I cheated. But it turns out simulated data are remarkably well behaved. Okay. So you want to talk predictors then? What predictors do? Time-invariant predictors, and then we can move on to time-varying stuff. So, did I do that? Okay. So back to the slides then. Time-invariant predictors, slide 50. Okay, good. Beware of missing predictors. So this is where I'm going to have to bum some of you out. So the rule is, in this software, any case that is incomplete gets dropped. If you are missing a predictor, that case is gone. So a case in this software is an occasion within a person. So incomplete occasions will be dropped. The model does not do anything with them. So this is less than ideal for time-varying information. The assumption that you're making in getting rid of incomplete occasions is missing at random. That's what MAR stands for, which roughly means that those cases would not have differed in any way from the ones that you observed for that person. So it's conditionally random after conditioning on the rest of their data. But if you have person-level predictors, time-invariant predictors that are missing, then the whole person is list-wise deleted, just like in least squares ANOVA. That's what happens. You have two options on how to fix this, and each of them has their own challenges. So this is an active area of research. I would encourage you to look at the work of Craig Enders now he's at UCLA, I think, on this topic. He wrote the Missing Data book that's very helpful, and he does a lot of research on this area. But here's the one that SEM folks will always say, well, wait, you can have FIML. FIML fixes everything. Nope. Only in certain situations. So the way that you can allow missingness on a predictor is to make the program think it's an outcome. And M+, that means listing its mean, its variance, or its covariance as an estimated model parameter. M+ thinks it's now an outcome, even if it's not predicted. What that means is that you've brought it into the likelihood so that those summary statistics are part of the algorithm that it's trying to find parameters to describe all of them. So when you make a predictor an outcome in this fashion, the good news is that You can have missingness on it. The bad news is that you then have distributional assumptions the same as any outcome. And it is only multivariate normal that you're allowed to trick this for. I have tried, and as of M+ version 8, the most current version, it still will not allow you to bring predictors into the likelihood and have them have missing data if they are not normally distributed. If you try to list them on categorical or count or one of the other link function statements, it will not do it. So you can have missingness on predictors if normality is a reasonable thing to assume for them. If that's not the case, your other option is the world of imputation. So multiple imputation in particular, you would never ever want to do any kind of single value imputation. But multiple imputation also has distributional assumptions. Any variable that has missingness, you have to specify a distribution for in order for the algorithm to do the imputation. So that means that you'd have to pick a software package that allows you to have choices for that if you have non-normally distributed outcomes. And the other thing that makes this particularly challenging in the world of multi-level is that when you have an imputation model, you are putting in predictors that are likely to be related to what the value would have been. Your imputation model has to have all of the information that you would expect to find in your analysis model. So that includes fixed effects, interaction terms, and all possible random effects that you might want to test. And you can't stick in all possible random effects without it blowing up. So how do you know that you have enough things in the imputation model, and how do you know that you have the right conditional distribution for all of that stuff? Those are the tricky parts. So what I tend to do is just not use cases with missing data, because that's the safest thing in terms of not making any additional assumptions. It does have the problem of diminished power. It does have the problem of missing completely at random for time-invariant predictors. Right now, there's really not good options, to be fair. So, sorry to bum you out with that, but I have to tell you that. Okay. I know. See, it fixes it like with an asterisk behind it, right? It fixes it if you're willing to make distributional assumptions. It handles it, exactly. You get numbers back. Yes. Yes. Yes, the M+ discussion board. So long as reviewer 3 is fine with you quoting a discussion board rather than a piece of peer-reviewed work, right? That's where the problem comes in. I don't know to what extent the assertions that they make have been backed up by published literature. So, yeah, I tread carefully, I guess. So, I had a question before break. Reviewer 3, that's just sort of like an inside joke with me because it's always the cranky one as reviewer 3. Like the positive people seem like they're listed first. So there's a meme about that on the internet too. It's not appropriate to share in this classroom, but if you ask the Google about it, you can find it. So, all right, so predictors then. So we're talking about time invariant first. The rest of the afternoon is time varying. So we're talking person things that you have either measured once. Basically, yeah, even if you think they change over time, if you only have one of them, it's invariant. So you either might need to make an argument as to why that's okay or limit your conclusions accordingly to the time that you measured it. This is also going to include between-person variation in your time-varying predictors. So we will see examples of that this afternoon. Just like time 0 needs to mean something, your predictors should always be centered so that 0 is meaningful. Common is grand mean centering, where you take the sample mean and use that as your centering constant. That's fine, but it's not necessarily any better or different than just picking any convenient value. So I tend to pick round numbers because then I can say my reference is, an 80-year-old person or someone with high school education rather than someone who's at the mean, where the mean is always a sample-specific number. Categorical predictors, some group's got to be the 0. So you can set it up yourself or you can let the software do it, but somebody's got to be the 0. So what do they do then? In terms of pseudo R-square, fixed effects of level 2 predictors by themselves, they capture level 2 random intercept variance. So if I have time-invariant predictor of, say, education, and I put that in the model, that's going to capture random intercept variance. If I have an interaction among level 2 time-invariant predictors, like let's say treatment versus control by education, something like that, that would also capture level 2 random intercept variance. What happens with cross-level interactions is the tricky part. So when you have a level 2 person-level time-invariant predictor interact with a level 1 time-varying predictor, like group by time, for instance, what happens in terms of the variance it accounts for depends on what type of effect the level 1 predictor has. So when you're interested in testing these kinds of effects, these cross-level, always, always, always test for this level 1 predictor to have a random slope over level 2 units first. Always, always, always. There is a literature on that that is not on the M+ discussion board. It's in actual papers. And type 1 error rates are way too high if you don't do this. The reason is because when you put an interaction term like this in the model, its purpose is to explain level 2 variance in this level 1 effect. So if I put group by time in the model, what it's trying to do is say why the time slope has a random variance. Why is it that people change differently? Well, part of it's because of what group they're in. So that's the variance term that this type of cross-level interaction is supposed to be targeting. Now, that being said, if you do test at level 2 slope and it's not random, it's not significant, it's debatable as to whether or not this is okay, but I am on the side that says that it is, then that cross-level interaction will explain residual variance instead. And we would have a different word for what the level 1 effect would be called, which is in the middle of fixed and random, but it's called systematically varying. So to show you what that might look like, here's an example with just a random linear model and an effect of education. So years of education, easy time-invariant covariate, centered such that 12 years is my reference. So this intercept then is going to be specific to time 0. So we can go through what the model says each person's intercept is going to be. So beta 0I is how each person gets an intercept here. It starts off with the fixed intercept. So previously this was at time 0. Now that we also have education as a predictor of the intercept, it is also for education of 12 years. So it's doubly conditional. This fixed effect right here, this gamma 01, that is the change in the intercept per unit change in education. So this is the main effect of education. Main effects always adjust the intercepts. U0 then used to be the difference between the fixed intercept and my intercept. It still is, but now the fixed intercept is the one that's given to me by this combination that also includes education. So you can think of U0 as how far off your intercept still is after adjusting it for education. So all people with 12 years of education get the same intercept. U0 then is the remaining difference between each individual intercept for a high school grad. So to the extent that education matters in predicting the intercept, U0 variance is what should go down. At this point, the terminology in other books, not mine, might change to call this a level 2 residual because it's left over. I'm not going to do that to you. This is a random intercept left over. That's what it is. Residuals are at level 1. Likewise, I can have education as a predictor of the linear slope, and it would look like this. So gamma 10 is going to be the fixed linear time slope, and it becomes conditional on education equals 12 because education is a predictor of the linear time slope. And it's kind of hard to see in this version of writing the model, but you can see it more clearly without the placeholders. Gamma 11 is the ed by time cross-level interaction. Ed is level 2, time is level 1. So this is the difference in the linear time slope per unit education. to the extent that education matters in predicting change, the U1 variance should go down relative to what it was before. So it's the remaining individual slope variation after giving each person a different slope as a function of education. So if we have then this random slope here, ed by time predicts it. If this random slope were not here, ed by time would predict E instead, because this random slope would have come out of E in the first place. So pseudo R-squared gets a little tricky when it comes to cross-level interactions. Okay. How are we doing? Is it time for more coffee yet? So do we have more coffee? Yeah, I think there's still some over there. So any of that you want to hear again or ask about? Yeah, so if this term is in the model, like it is here, U1 is all the reasons why people need their own slopes. This is saying part of that's because of education. So the U1 variance, the random slope variance, should go down after we put this education by time effect in the model. If this is my hand is going to do any good. If this is not here, then we put this term in right here. The only thing for it to do is to predict E instead. All right. I think that's, and here's an example with a quadratic like we're about to have. So this would be the same idea, but with a random quadratic model. Each person gets their own intercept. Each person gets their own linear slope. The only catch is that this linear slope right here is specific to time 0, given the quadratic effective time. And then we can have the same pattern for the quadratic. So seeing all of these subscripts helps to illustrate, I think, how they make sense. So in the gamma fixed effects here, the first subscript refers to which beta it goes with. So in this first row, all of these terms are predicting beta 0, and that's why they all start with 0. In this second row, all of these terms are predicting beta 1, and that's why they all start with 1. And all of these terms in the bottom are predicting beta 2, and they start with 2. Within each row then, the second subscript is an indicator for which predictor you're on, where they all start with 0, because that's what you get just from adding that fixed effect at level 1. So 00 is the intercept. 01 is the first predictor of the intercept. 10 is the fixed linear time slope. 11 is the first predictor of the linear time slope. 20 is the quadratic time slope. 21 is the first predictor of the quadratic. And that's what it looks like all together again. So whether you write out equations in this composite form or whether you do it as multi-level is up to you. This way can be easier to understand if you have a very complicated model, whereas this way looks more like what you would expect from a typical linear mixed model sort of representation, like what you'd see in stats. All right, that's it. Yay. So let's finish that example so we can move on. So any questions on that? Sir? Yes, so the question was, did I say you had to test these random slopes first before adding cross-level interactions? That is exactly what I said, yes. So this is why. This is what this is for. So more generally in these equations, the job of any fixed effect is to predict the term that's in its line. So when you first add time, you're trying to capture E variance. When you add time squared, you're trying to capture E variance. When you add ed here, you're trying to capture U0 variance. When you add ed here, This is ed by time. You're trying to capture time slope variance. So if you don't have this in the model, like that, this has two consequences. The standard error for this cross-level interaction is going to be too small because it should have this extra variability in it. It's also going to use different degrees of freedom. And so this has a higher chance of having a type 1 error because what you're saying then about this effective time is that after controlling for education, it's fixed. There's no more differences, and that's a very strong statement. So yeah, get that back. Other questions? All right, and one last model to look at. Following the example in Chapter 7b, I added a time-invariant predictor of mothers' attitudes about smoking and drinking as measured at age 12, another fictitious variable in my study here. So more conservative means higher scores here. So it was on a scale of 1 to 5, and that's why we have a mean of about 4. Mothers are fairly conservative. Not something I have to worry about yet. My 3-year-old has not approached me about smoking or drinking. So I added this attitudes predictor 3 different ways. Gamma O1 here is its main effect. Gamma 1,1 is its interaction with linear time. And gamma 2,1 is its interaction with quadratic time. And there they all are. So then thinking about what kind of variance each of these is going to predict, the main effect of attitudes right here should capture this U0 variance. So part of the reason for individual differences in risky behavior at age 18 is mother's attitudes. Likewise, this attitude by linear time cross-level interaction gamma 1,1 here, part of the reason why girls grow linearly at different rates is because there's mother's attitudes. But then this last one, this is the tricky one. There's no U2 here. It's not here. We just tested it and found we don't need it. So to me, you are justified in leaving it out and still testing whether or not the effect of attitudes what moderates this quadratic term, and the residual is what it would reduce in this case. If this were to be significant, the way that I would talk about it is with the phrase systematically varying. So we have fixed and random from the morning, right? Fixed is everybody gets the same. Random is everybody gets their own. Systematically varying is the middle. In this example, what this would mean is that the quadratic slope does not vary randomly across people, but it does vary systematically as a function of mother's attitudes. So it's not completely the same, and it's not completely everybody gets their own. It gets their own as a deterministic function of a predictor. That's what I would call that if this were to be significant. Okay. Survey says, for those of you who were not alive in the 80s, by the way, that is a game show reference. Family Feud, the original. So here's my 3 new fixed effects. So in interpreting this model, the first 3 terms that were there before, the fixed intercept, fixed linear, and fixed quadratic, those are now all conditional. Because of the 3 effects of attitudes, they are all specifically for a child with a mother attitude score of 4. So if we start with the intercept, look at just those 2. This main effect of attitudes, it's as if it's interacting with the intercept. So whenever you see a level 2 main effect sitting there by itself, like mentally, think of it like that. Then it'll make it clear what it's doing. Okay. So would anyone like to play along? Interpret the coefficient of negative 3.5. No one wants to play. sir. Go down because it's negative. Yep. Perfect. Thank you. Yep. The negative's hard to tell, but yes, that's exactly right. So it's the expected value at age 18 specifically is lower by 3.5 for every unit additional mother attitude. So less risky behavior in children of more conservative parents at 18. Let's do this one, practice with two-way interaction terms. So this is the linear slope at 18 for somebody with attitudes of 4. It's positive. The interaction of that linear slope with attitudes is negative. So which pattern is this? The interaction term makes the main effect more positive, less positive, more negative, or less negative. Which is it? Less positive. Very good. So yeah, the linear slope is significant and positive in people who have attitudes of 4. It becomes significantly less positive by 0.9 per unit attitude. Yeah, I would take that, less problematic behavior the next year, or it's a lesser rate of growth, so a lesser increase. Yeah, there's lots of more intuitive ways to say less positive, but the less positive is important because they're still going up. They're not going down. They're going up less. And the very last one, even though this is by most people's standards non-significant, I like all the different euphemisms for a non-significant: trending, marginal. My personal favorite is approaching, because it makes it sound like if you just come back and check on it later, it will be there. It's approaching significance. Give it a minute. So if I do that one, it's the same pattern. This is another less positive. So the rate of acceleration is less positive by 0.06 per unit attitudes. So overall, it looks like there's a dampening pattern of attitudes. And here's a picture. I made this in Excel using the model parameters. But the difference in the quadratic is non-significant, so we'll keep that out of the model. And then last but not least, effect size measures. So the main effective attitudes captured 16% of the random intercept. The interaction of attitudes by linear time captured 16% of the random linear time slope variance, and attitudes by quadratic time captured 0.3% of the residual. If you want to put that all back together again, what is the net effect of attitudes across the whole model? Well, here's the previous model that had just time. That was an total R-square of 19.19. Now I'm up to a total R-square of 0.23, so I picked up about 5% more variance. So attitudes accounted for 5% additional variance overall in risky behavior. The specific ways in which it accounted for that 5% are right here. Questions on that story? All right. So now I want to show you what this exact same model that we just finished is going to look like in M+. Because their code is non-trivial to understand as a first pass. So this is the packet that is in landscape, separate packet. First the MLM version, then potentially the SEM if time permits. Okay. So for how many folks is this brand new? MLM. Quite a few folks. All right. So let's go through this here. I have comments to try and explain what this stuff means. It is non-intuitive relative to the same version of the model specified in mixed model software, which is why I never start here. But unfortunately, to do all the cool stuff that involves multivariate outcomes, we have to use this software instead. So first off, in M+, you can't use regular data files. You have to convert it into text files of some kind. So in the Piles of Variance website, there's examples on how to do that. I prefer to make CSV files rather than DAT files because they're easily opened in Excel, so I can check to make sure they're okay. I would say that about 60% of the time when people come to me with badly fitting models and they want my help troubleshooting it, it's because M+ never read their data incorrectly. At least 60% of the time, a conservative estimate. That's because M+ does not tie the names to the variables. You have to do it for it. So there's no variables at the top of the file. And this statement right here, this names, this requires you to list in the exact order in which they occur every single variable name. It is easy to screw this up. So I always cut my files down to just the few that I need to make it easier to not screw this up. I also get rid of any dates, any strings, any special characters, any of that stuff. Those variables have to go or it won't read it correctly. Then we have the use variable option says which variables are in the model. If you forget this, it will think all of them are in your model, including person ID. Bad things can happen. You have to tell it what your missing data indicator is. Technically, it will take blanks or commas. I have had very bad luck with that, and so I'm superstitious and insist on having always an identifier. These options are unique to doing multi-level modeling in M+. You have to be able to tell it what your ID variable is. So in a 2-level model, you would only list one. I'm not going to do any 3-level examples for you, but I have them. If you're interested, I can send you some code. These 2 variables then are where you list level-specific variables. So if it's only level 2 or only level 1. So in the example that we're dealing with, I have age and I have age squared, which I had to make as a predictor as within level 1. Attitude centered at 4 is only level 2. So this stops it from trying to find variance for it at another level at which it doesn't belong. So level-specific variables, whether they're predictors or outcomes, go here. The type of analysis that you're doing, 2-level random, estimator equals maximum likelihood. So this is the FIML, the full information. It does not have REML. Another option that you can use is MLR, which is robust maximum likelihood that corrects for non-normality. I'm not doing that for continuity with the other programs, but you can certainly do that on your own. And this is the exact same model that we just finished with. So there are 2 statements that differentiate the levels, within and between, with percent signs around them. M+ is not case sensitive, but I always write it that way. So in these models, when you list a variable all by itself, you are referring to its variance. Whether it should be a variance or a variance left over, a residual variance, M+ understands based on the context of the model, so you don't have to worry about that. So as I said before, I write everything out, even the stuff that's estimated by default. So when I write risky, what I'm actually referring to is its variance in the level 1 within model. So this is level 1 residual variance right here. I am giving it a label. Things in parentheses are labels. You can use those to help you calculate other quantities or just to keep track of stuff. The next two lines are non-intuitive unless you look back at the equation that describes this model. You see how we have these beta 1 and beta 2 placeholders here? They're not things, but they hold the place of things to be defined later. That's what these are. So our slope is a name that I've given that represents beta 1. Our quad is a name that I've given that represents beta 2. It is defined as the regression of, and it always goes y on x. So it is age predicting risky or age squared predicting risky. So that regression effect is named r slope or r quad. You can name it whatever you like, so long as you stay within 8 characters. Because M+ is state-of-the-art when it comes to everything except data syntax. In the between model then, same rule as before, variables listed by themselves refer to their variances. But now when I write risky in the between model, I'm actually referring to its level 2 intercept variance instead. And so I have r_int_var as my label here just to help you out. Same thing when I refer to r slope right here. That is its variance. Note that I have r quad and then an @0. Because in the model we just finished, there was no random quadratic variance. The U2 is not here. So you have to actively shut it off in M+. And you shut it off by doing an @ sign and a 0. Questions so far? Okay, the terms in brackets. These are either going to be means or intercepts. They are means if they are not predicted by anything, and they are intercepts if they are predicted by anything. So when I write risky in brackets, I'm actually referring to the fixed intercept for risky. Likewise, when I have r slope and r quad in these brackets, this is my fixed linear time slope, and this is my fixed quadratic time slope. Not estimated by default are any covariances among my random effects. So I'm adding that here. With means a covariance. So risky with r slope is the covariance between the intercept and the slope for risky. And last but not least, an example of another regression. Here is attitudes centered at 4, predicting the intercept, the linear slope, and the quadratic. So there's only 4 words, I think, 3 words that you need to learn in M+ in terms of not variable names. On is a regression, and I always got these backwards in terms of which goes first until a colleague gave me a tip. Think of on as equal. Like y equals all the x's when you write out an equation, then you'll get it right. So if we count up all the parameters that are being estimated, there's only one that's being estimated in the within model, and that's this risky residual variance at level 1. At level 2, we have 6 fixed effects. Fixed intercept for risky, fixed linear slope, fixed quadratic slope, and then attitudes predicting each of those 3 things. So that's gamma 01, gamma 11, gamma 21. Variances then, we have risky intercept variance right here, risky slope variance right here, and a covariance right here. questions on any of that? Now the output. No matter how you list your stuff, it always lists it in the order it wants, starting with ons. Actually, bys, then ons, then withs. So I have the two packets because I thought it might be easiest to compare the numbers across the two. So give me 1 second to set up two screens here. Okay, so I have the output from SAS from the very last model next to the one from M+. This is the same model. So we have 10 parameters, 10 parameters. Log likelihood in M+. That's your HO value, that's yours. So minus 3799, minus 3799 times negative 2 is 7599. And if you don't want to do the math and you want to make sure that your model is actually the same, AIC should match. 7619, 7619. Because AIC and BIC are always phrased as smaller is better. Model results then. Within level. Residual variance for risky, 8.3. That shows up over here as your residual in the R matrix. Between level. First are your ons, so the effective attitude on the linear slope, attitude on the quadratic slope, and attitude on the intercept show up here, here. Note the rest of the output though. This gives you a column for your estimate, your standard error. Estimate divided by standard error is right here. That thing it's considering to be a z, whereas SAS considers it to be a t and uses this degrees of freedom to generate a p-value. So the p-values may not match exactly because this is assuming infinite denominator degrees of freedom instead. Risky with R slope, that is my covariance between the random intercept and the random linear slope. And last but not least, more fun with labels. So it has 3 intercepts. Only one of them is the intercept. Job security, folks. So the one that you would think should be the intercept is right here. This is the fixed intercept for risky. That matches. These things are the fixed linear slope and the fixed quadratic slope. It's as if this is the beta 1 and the beta 2. The mean of those new variables should be its fixed effect, and the variance around it should be its random effect variance. Because these are all being predicted by attitudes, they are called intercepts. If they weren't being predicted by attitudes, they will be called means. So you can think of this as the average linear slope, specifically for someone with attitudes of 4. This is the average quadratic slope, specifically for someone with attitudes of 4. And then residual variances. So it doesn't mean residual in the context of level 1 residual. It means it in the context of leftover. So you will get a variance if it's not predicted, and you will get a residual variance if it is predicted. So this risky right here is random intercept variance left over. Our slope is random linear slope variance left over. And our quad was the variance that we fixed to 0. And that's why it says it has an estimate of 0, a standard error of 0, and then these things mean you fixed it. I can't give you a test. All right, go back. So any questions on linking M+ to other packages or how to set up things? Yes? These things, brackets. So this is how you refer to it's either a mean or an intercept. Where a mean is it's for a variable that is not predicted, and an intercept is for a variable that is predicted. And what this refers to is the mean of these new variables that you've created, where the variable itself is the representation of this fixed effect. So it's like the mean of this term is the fixed effect for this term. The variance around it is the random slope or intercept variance that goes with it. So when I put risky in brackets, that's my fixed intercept. That's gamma 0, 0. When I put risky without brackets, that's the random intercept variance around it. And likewise, our slope in brackets is the fixed linear slope. Our slope, no brackets, is the random slope variance around it. Our quad in brackets is the fixed quadratic slope. Our quad at 0 means don't put a variance around it, keep it fixed. What it does automatically is everything but these 3 lines in level 2. In level 2, any terms that you define at level 1 automatically get a mean and a variance. So you have to shut off either one that you don't want. You have to put any specific ons you want in, as well as covariances between the random effects. At level 1, all variables that are not listed on either within or between automatically get a variance here too, and these are things that you have to define. Okay. Other questions? So why would I do it in M+? No reason. Absolutely no reason why you would have to do this model in M+. The only possible reasons would be to get a robust estimator, which you can get out of SAS or Stata as well in terms of robust standard errors, or to be able to introduce missingness on a predictor. So let's say that attitudes here had some missingness and it was plausibly normal, so I was okay with faking it into being an outcome. If I wanted to allow missingness on attitudes, turning it into an outcome so that it had a distributional assumption and then you could have missing at random on it, it would look like this. The end. All you have to do is list either its variance, its mean, or its covariance with something, and that brings it into the likelihood. So then its parameters have to get found along with those of risky, and it can have missingness on it, if you're willing to assume it's normally distributed. Okay. Other questions? So I have 2 suggestions for where to head next. What time are we supposed to have a break, by the way? Is that coming up? Look. 2:40. Oh, very soon then. Well, we may start a few minutes early after I take this informal poll. We can either dive into time varying stuff, or I can show you how to fit this exact same thing as a structural equation model. Anybody have a preference? Time varying? All for time varying, want to take votes? SEM side? Okay then, I know who I'm talking to. All right, let's take our break a few minutes early and we'll come back and play time varying.